Continuing with our discussion on the conservation of energy, let's look at example 2. Say we want to construct the conservation of energy equation for an incompressible fluid flowing through a throttle, which has a constant cross-sectional flow area at both our inlet and exit, operating under steady state. First, we begin by writing the continuity equation. The time rate of change of mass within our system is equal to the sum of our mass flows in less the sum of our mass flows out. Since our system is operating under steady state, the time rate of change of mass within our system is identically equal to 0. Thus, the sum of our mass flows in is equal to the sum of our mass flows out. Since this is a single stream device, we can express our continuity equation as m dot 1 is equal to m dot 2. That is, our mass flow in to our throttle is identically equal to our mass flow out of our throttle. Next, we will construct our conservation energy equation. We are going to make the following assumptions. Our device is operating under steady state, that is, the time rate of change of energy within our system is equal to 0. We also assume that no heat is added or removed, such that Q dot tends to 0. And we also assume that there is no work done onto or by our throttle. W dot is equal to 0. Our next set of assumptions is that our kinetic energy change is equal to 0. That is, V1 squared per 2 is identically equal to V2 squared per 2. And there is no change of potential energy. That is, Gz1 would be equal to Gz2. Recognizing that our mass flow into our system is equal to our mass flow out of our system, i.e. m dot 1 is equal to m dot 2, we can divide out, and all we are left with is the difference of enthalpies. That is, H1 would be equal to H2. Now, one main assumption is that our velocity at our inlet is equal to our velocity at our exit. And this comes from our continuity equation. If we express our mass flow rates in terms of our density, cross-sectional flow areas, and velocities, we see rho AV evaluated at our inlet has to be equal to rho AV at our outlet. If we assume our cross-sectional areas are constant, A1 and A2 are equal. Thus, if we divide out, that term becomes unity. And if we assume our density at our inlet and exit is also equal, V1 is equal to V2. That is, we have to assume our density is not a function of temperature or pressure for this formulation of the conservation of energy to hold true for a throttle.